The second most abundant element on Earth begins its journey after reacting with oxygen, starting from sand, particularly quartz sand. Most solar panels are made of silicon, which is the primary component of natural beach sand. Silicon is extremely abundant, making it the second most available element on the planet. After oxidizing, its journey continues from the quarry to the furnace. The first step is extracting silicon from rocks. This is done in a massive furnace where temperatures exceed 2000 degrees Celsius, an incredibly hot and rather dangerous environment. Silicon is used to make everything from window glass to the processor in your home computer. Without it, solar panels wouldn't function. Purified silicon is melted and formed into ingots, which are the raw material for solar wafers. These ingots are produced using either the Czochralski CZ process or the float zone method. In the Czochralski process, a seed crystal is dipped into molten silicon and slowly pulled out, forming a cylindrical ingot. This block is too large to place on your rooftop, the usual destination for solar panels, so it needs to be resized. Using a wire saw, the silicon ingot is sliced into thin wafers. This precise process minimizes material loss. These wafers are typically less than 200 microns thick. After surface treatment to remove remaining impurities and defects, an anti-reflective coating is applied to the front surface of the wafer to enhance light absorption and improve efficiency in converting sunlight into electricity. A drying process ensures optimal surface cleanliness. Then, fully automated sensors and cameras measure all wafers and grade them according to thickness and surface quality. In the next step, each wafer is turned into a solar cell capable of converting sunlight into electricity. Metal conductors, usually made from silver or aluminum, are screen printed onto the wafer, forming a grid-like matrix that ensures even current distribution. The wafer is then processed in a high-temperature furnace, where phosphorus diffusion occurs at the surface, creating a negative charge that combines with a boron-doped layer. This forms the essential p-n junction needed for a solar cell to function. After this intense 6-year journey through chemistry and physics, we now move to the exciting part, solar cell assembly. Individual solar cells are interconnected to form solar panels. These panels can be configured in various layouts depending on the desired output and application. The cells are typically soldered together using conductive adhesives or laser welding to create series or parallel connections. Once interconnected, the cells are encapsulated in protective layers, usually made from ethylene vinyl acetate (EVA), to ensure durability and weather resistance. A junction box containing diodes and connectors is attached to facilitate electrical connections. Now comes the fun part. All finished modules undergo a series of rigorous tests to ensure their durability and reliability. Starting with infrared cameras, initial tests inspect for microcracks at the cell level to guarantee structural integrity from the start. The modules then undergo flash testing to measure performance under standard operating conditions. Next is the mechanical load test, which simulates harsh environmental conditions, such as strong winds, heavy snow, and static pressure like ice buildup. This test assesses the panel's resilience and ability to withstand extreme weather. Impact tests follow to evaluate durability against strong collisions, ensuring they can handle unexpected events without losing function. Innovative proprietary tests, like high acceleration stress testing, are used to understand how materials age over time, offering priceless insights into long-term performance. Further infrared testing is conducted to analyze the module's temperature, behavior under direct sunlight, ensuring optimal thermal management. Finally, each module undergoes 8 different tests to assess performance under high humidity, intense UV exposure, and various extreme weather conditions, including heat waves and hailstorms. After all testing and quality control procedures are complete, the packaging materials are carefully chosen to ensure full protection during transport and storage. Solar panels are usually transported using pallets or containers with proper labeling and cushioning for easy handling and installation. Understanding commercial solar panel manufacturing helps pave the way for the next exciting step: building your own DIY solar panel, a project that can be both fun and rewarding. With the right outline, this process becomes manageable. Let's break down each stage further. First, designing the layout, assessing available space, and selecting the appropriate type of solar panel are crucial first steps, regardless of your choice.